Right, hello, my name is Mortenson, and I'm going to be presenting some work based on my PhD entitled Modeling the Arctic Ocean Carbon System. This work has been with Nadia Steiner, Hakase Hayashida, Tessa So, Adam Monahan, and Joanna Laenger is a new PhD student who's going to be following up on this work and working with future projections. What I have to show in this first title slide is the going clockwise, the CO2 flux, the ice concentration, the ice algae, and the phytoplankton as monthly products from the beginning of the model run in 1980 through to the end of the model run in 2015 to give just an idea of what is available in this model, in this output. So moving on. Okay, in order to illustrate how the Arctic is important in terms of climate change, I'm introducing this figure dramatically titled the Arctic Sea Ice Death Spiral. It represents, through biomass, which is a reanalysis product, the Arctic sea ice volume over the period of the recent satellite observations from around 1979 to the present day. And you can see through the different colors which represent the different months how for each month the sea ice volume has been decreasing over this period. And this is particularly true in the black line, which represents the sea ice minimum in September, which drops from approximately 17,000 cubic kilometers at the beginning of the period to less than 5,000 cubic kilometers by the end of the by the present day. And along with sea ice loss, well, we know that this sea ice loss is projected to continue into the future. And along with this sea ice loss are accelerated changes in multiple physical and biogeochemical properties, including pH, aragonite saturation state, temperature, sea surface temperature, etc. And so this leads to the question, how do models in concert with observations help in the understanding of Arctic changes? We all know, of course, that observations are essential in the model development and validation. But these observations can't be everywhere and can't be all the time, especially in the Arctic due to the remoteness of the area and severity of the climate. So well-constrained models can fill in gaps of these observations and provide information about regions and times with high uncertainty and/or high variability. The results from these model simulations can inform when and where new observations might have the most impact, leading us back to the beginning of this train of thought. Just a brief description of the model that we are using in this study. It's forced with an atmosphere based on the Drakkar forcing set. And the ocean and sea ice physics are represented through NEMO, or the Nucleus for European Models of the Ocean, and LEM2 for the sea ice. The ocean biogeochemistry is represented through the Canadian Ocean Ecosystem Model, or CANOE, which is in the process of development at the University of Victoria. And we've added two implementations, namely the sea ice algae and ice carbon pump. Sea ice algae is a new functional group within the ice, and the ice carbon pump is supposed to represent the rejection of high DIC, high TA brine during ice growth and the release of low DIC, low TA ice melt during the melting process. So the implementation of the model ecosystem, as I mentioned, it has ice algae and nutrients within the sea ice, which is above the blue line. Below the blue line we have two different functional phytoplankton groups, same for zooplankton, representing large and small. The large phytoplankton are supposed to represent diatoms, and small phytoplankton as dinoflagellates, which are consumed by the large and small zooplankton respectively, all of which produce large and small detritus respectively, and the nutrient currency is nitrogen in forms of nitrate and ammonium. In order to show how we capture the physics of the ice evolution over the recent sea ice loss, I'm presenting here the area of Arctic sea ice in the upper figure and the volume of Arctic sea ice in the lower figure. The dashed and solid lines represent the simulation of our model over the period 1980 to 2015. And the dotted lines in the upper figure represent observations based on satellite measurements by National Snow and Ice Data Center. the maximum and minimum of those values. And you can see that we capture the variability over the period in the upper figure. The lower figure shows, again, the dashed and solid lines are our simulated output, and the dotted lines are the maximum and minimum of the biomass that I mentioned earlier, sea ice volume. And you can see that we capture both the variability of the ice volume as well as the decline over the recent period. Moving on to the carbon system, the upper figure shows in the black solid line the annual Arctic Ocean carbon uptake, which over the period covered increases from 110 to 140 teragrams carbon per year. The dashed line is the monthly average, and the different colors represent the different seasons, red being summer, blue being winter. The second figure shows PCO2 and the Pan-Arctic average in black, as well as the atmospheric value in red. And the lower figure shows the pH decline in the annual average from 8.1 to 8 over the period. However, that comes with a caveat that there are large seasonal and regional variability in all of these variables output. In this figure, I'd like to show the differences between the standard run and the no ice algae and no ice carbon pump runs to highlight the importance of the implementation of ice algae in the ice carbon pump. You can see in the upper figure, similar to the previous figure, the solid lines represent the seasonal carbon uptake, whereas the dashed and dotted lines represent the no ice carbon pump and the no ice algae run. You can see a consistent negative offset in the no ice algae run relative to the standard run, which accumulates over the period, leading to a drop in the net carbon uptake by the Arctic Ocean by the end of the 35-year run. Sorry, 35-year run. In the next figure, you can see that although there's not much difference in the Pan-Arctic sea surface DIC and TA between the standard and no ice algae runs, there's a substantial decrease in the seasonal variability when you compare the no ice carbon pump run to the standard run. And finally, in the lower figure, you can see the omega aragonite saturation state, which shows a negative trend for all variables, for all runs, but a large increase in the summer value for the no ice carbon pump and a decrease in the summer value for the no ice algae run. Next, to highlight the regional variability, I've picked 6 regions which deviate from the Pan-Arctic mean in one or more of the figures on the right. So we see in the bottom left figure, going counterclockwise, the Canadian Polar Shelf or Canadian Arctic Archipelago, the South and North Beaufort Seas, the Laptev, Barents, and Norwegian Seas. And the same color coding is used on the figure to the right, which shows the black solid lines represent the Pan-Arctic mean or total, and the dashed black line in the upper figure represents the atmospheric PCO2 value. We can see large variabilities, which is what I want you to take away from this figure, in many of the regions. And in particular, there's high carbon uptake in the Atlantic sector, which you can see in the second panel, specifically the Norwegian and Barents Seas. And there's low pH and high PCO2 in the Laptev, North and South Beaufort Seas, which you can see in the lower 2 figure panels, middle and upper and third panel. Lastly, I'd like to present the aragonite saturation state in the Beaufort Sea. This is being used for both summer and winter in a collaboration with Nina Bednarsek, who's assessing the aragonite shell dissolution in the Beaufort Sea. So this is just one example of how this data set can be used in other contexts. So lastly, where is this work going? We'd like to continue the model analysis to assess details in the spatial and temporal changes in the ocean carbon sink, as well as states of the ocean acidification, with a focus on the Canadian Arctic Archipelago. But of course, Pan-Arctic model output will also be available. We'd also like to evaluate observation-based approaches for estimates of annual carbon uptake in the region via reproduction of the approach in the model. And finally, we'd like to extend the model for future projections using forcing from the Canadian Regional Climate Model, KNRCM5, and evaluate spatial and temporal variability in the progression of ocean acidification, and link this with multiple stressors and species impact assessments. So with that, I'd like to say thanks not only to the co-authors of this paper, but also with help from Andrew Schau, Belaine Moa, Arlen Dirksen, and we'd all look forward to seeing Johan Laenger's follow-up with the future projections. And I'd like to guide your attention to the two publications on the right, which come from this research, as well as encourage you to contact me at eric.mortenson@CSIRO.au if you have any questions or comments about this presentation. Thank you very much.